Thanks. Welcome everyone. Welcome back. Hope you guys have a good lunch or break. Hope you're enjoying the hotel so far. So this session is a technical session B, routing and switches. So again, I will, we have two presentations in this session, and I will play the video, then I will post the Slack channel, the link to the Zoom chat here. And please ask your question, post your questions in the Slack channel, and we will have around 5 minutes for QA for each presentation. All right, let's go with our first presentation. So our first speaker is Cristobal Camarillo. He received a master's degree in computer science with distinction in 2011 and a PhD degree in 2015, both from the University of Cantabria, Spain. Currently, he is a researcher in the University of Cantabria. His research interests include the graph theory with applications to interconnection networks and coding theory. So he's going to present the paper, Polarized routing and efficient and versatile algorithm for large direct network. So let me share my screen and play the video for you guys. Just a minute. All right, I hope you guys can see the screen. So let's get started.
This is the presentation of Polarized routing, an efficient and versatile algorithm for large direct networks. I am Cristóbal Camarero, and this work is co-authored by Carmen Martinez and Ramón Meivide, the three from the University of Cantabria in Santander, Spain. This is a topology agnostic routing mechanism for the large network used in data center and high-performing computing. We shall begin motivating why such mechanism is important. Then we explain the properties we look for in a routing algorithm and how it can be implemented, followed by some evaluation to show the routing effectively performs as expected, becoming a solution for many scenarios. And then we will conclude it all with a small discussion. Supercomputer and data center can be very large systems, with an usage that varies greatly depending on the running application and the activities of the user. The network must be able to provide the large bandwidth required for some application and the low latency required for others. These requirements must be fit within the imposed budget. This becomes more constraining in large systems because as the size of the system grows, the fractional cost corresponding to the network becomes more significant. The topology defining which links connect which routers determines how can be these properties. Nevertheless, it is necessary to include a routing mechanism able to exploit the topology to effectively provide the application with a high bandwidth and low latency. In the figure, we can observe a random regular graph of 16 routers, shown as square boxes. Each router is connected to other 4 routers. This topology is a 4 regular random graph. Each router has a couple servers attached. Thus, this tiny example has routers of radix 6. Now, we observe 2 minimal paths between 2 routers. They are of length 3, equal to the diameter of the graph. The routing algorithm looks for some route for each packet, but it does not necessarily choose a minimal path, and there are many strategies to choose them. The most abundant topologies are variants of other closed networks, also called fact trees. These are very well understood and with many good properties. However, especially when using high radix network, low diameter topology can reach greater bandwidth with lower cost. Of course, for any of these topologies, it is necessary to equip it with the router algorithm and to decide other matters such as their physical layout. There are lots of proposals of these topologies. Some listed in the slide, from the flattened butterfly to the dragonfly plus, and each proposal has included a router proposal. Routing topologies are especially notable because they reach a very good throughput per cost, although they present difficulties in aspects such as routing and layout. Indeed, our Polarized routing proposal is centered on random networks, as they are the harder case, but they also work in the others above. Routing algorithms can be grouped in two categories: the source-based routing, where all decisions are made in the feed router or generating server, and the hop-by-hop routing, in which all routers can make decisions on the taking path. The UGAL mechanism decides sources whether to use minimal or valiant depending on the occupation of the involved queues. For random regular graphs, it has been proposed to use the k-shortest path and several variants, with k commonly chosen to be 8. One of the k routes is chosen as the source for each packet. This source-based mechanism can work well when the relevant information is available at the source at the time, but it may perform worse if the state at the source is not representative of other regions or when the state changes too quickly. Under those situations, it is better to employ a hop-by-hop routing algorithm able to make several decisions on the fly, adapt to the circumstances. For example, the algorithm by McDonald for the HyperX is quite close to perfect in all cases. The presently proposed Polarized routing is a hop-by-hop routing algorithm agnostic of the topology, able to perform very well in all low-diameter networks. This includes the hard case or random networks, and as we shall see, matches the performance of the previous algorithm specifically designed for HyperX. Some progressive routines allow to reroute the packets when there is contention and then continue minimal to destination. Doing that can cause the route uses from source to destination could not be used in a mirrored way to route from the destination to this source. An intuition to see why this property should be looked for is that some routes are optimal for a given traffic pattern, then the reverse of those routes will be optimal for the reverse traffic pattern. In the figure, we see some routers as circles. If S is a source of a packet which has T as destination, then the blue path is the minimal path. The reversed path is the minimal path from T to S, so it's natural to have also available. Now, a longer path is shown in green. The symmetry property says that the reverse should be a valid path from T to S. We see here with the links in the opposite direction. And since the drawn topology is symmetric, we should expect to also have the path starting at S in the way this path is starting at T. As we see now. Random topologies usually do not have symmetries, so the beginnings and some routers are not trivially translated to other routers, but the reversing of the path should hold. The routing scheme proposed by Valiant about 40 years ago consists on routing each packet to a randomly selected intermediate router. Both segments done minimally. This scheme makes the final routes almost independent of the traffic pattern, so it's helpful for adverse traffic. However, sometimes it makes completely unnecessary hops, as can be observed in a cycle. The figure shows the situation where the bottom router 2 is the source of a packet with router 4 as destination. The randomly selected intermediate router is the router 0. The problem now is that minimal route from 0 to 4 goes through router 2, effectively undoing the first two hops, which have been better not done at all. The only route that makes sense to follow once the packet has reached router 0 is to follow the red line. The cycle is of course a story example, and more generally, the routing algorithm should avoid to revisit routers or other kind of redundant hops. The name of polarized routing comes from this symmetry between source and destination, as we make the source to effectively behave as a repulsive pole and destination an attractive pole. This concept is materialized as having for its term regarding the destination a symmetric one regarding the source. Resetting the routers is avoided by using the given wave function mu, defined as the difference of the distance to source minus the distance to destination. Note the symmetric usage. This function mu is lowest at the source and greatest at the target or destination, being its maximum value the distance from source to destination. In the figure, we see one polarized route colored, starting at -4 at the source router in the left and finishing at the destination in the right. Each hop increases mu by 1 or 2. The third hop crosses the bisection, the mu becoming positive. The fifth hop reaches the destination with a mu value of 4 as 4 is the distance from S to T. The symmetric usage of source and destination has some implication on the routing table. In typical hop-by-hop routing, the routing table is accessed to the entry corresponding to the destination, to get which port advances towards it. However, in Polarized routing, we index the routing table with both source and destination, and combine the two values to find which port are actually beneficial to take. We make a further extension to the table, which is to provide information about whether the neighbor is closer or farther by the same distance than the entry is, instead of just about being closer. This is, we store in the router table containing the router C is corresponding to the router X, and for P, a -1 when neighbor is closer to X, a 0 when the neighbor is at the same distance to X as before, and a 1 when the neighbor is farther from X. We also denote it as whether the neighbor approaches X, revolves X, or departs X. Moreover, we take different notation of delta X to mean the change in the distance to X by that hop. The figure illustrates the second hop in the route, which increases the distance to source by 1 and decreases the distance to destination by 1. Both values are obtained from the same routing table. Thus, we make two accesses to the routing table, one for the source and another for the destination. Each of these accesses having 3 possible values. This gives a total of 9 possibilities that we can show in the table below. The hops beneficial to take are colored green and the regressive one in red. The greenest possibility is the one of the hop getting away from the source and closer to the destination. This is what happened in all the hops in a minimal path from source to destination. The yellow ones will only be taken under the condition to be explained later. We also indicate in a superindex the magnitude of the benefit. This is the hop difference of the mu function. This delta mu is just delta S minus delta T. Hops with positive values will always be valid, and negative ones will always be forbidden to take. The increments of mu to determine which hops to take can easily be computed by using the routing table. The table of the router is accessed twice, one at source and one at destination, giving 2 vectors. These vectors are subtract and positive values are considered candidate ports to which to request. The value is also used as a priority, as the value 2 is the one found in the host of minimal path. We proceed to explaining the previous yellow colored cases corresponding to an unchanging value of mu. It is easy to see that some of these links are part of the shared routes, especially at the beginning and end of a route. For example, in a cycle the non-minimal path starts with one of these. However, a careless use of them can cause live lock or unbounded routes, and is necessary to add mechanisms to control it. We decide to break cyclic dependency by allowing this to get away from source when closer to it and to get closer to destination when closer to it. This is, we forbid links that approach both when closer to a source, and we forbid to depart both when the packet is already closer to the destination. In the figure, yellow links are vertical with no change to the move function. The first yellow is a worse, as it gets away of both source and destination, and is allowed as it is closer to the source. The second yellow link is downwards, as it gets closer to the end, which will allow as it closer to the destination. We have described which links are valid for polarized routers, but also noted a priority that needs to be considered in the router. We have coupled the increase in the function mu with the number of packets in the associated queues. This is similar which is done in other mechanisms such as UGAL to discriminate between using minimal and valiant routes. We get penalization to the different links in function of mu. To the greatest increase we set no penalization. To the second, a penalization of 4 packets, and to the third, a penalization of 5 packets. A selection of these values depends on the size of the queues. In the bottom left of the figure, the current router has 3 valid polarized links. For each link, we have an associated output buffer of the current router and an input buffer on the neighbor router. We add the occupation of both queues using a credit counter as proxy of the latter. We further add the penalization to this occupation. Then the request is performed to a queue with minimal value. The yellow candidate has a total of 5, which is less than the sum of the two others. Therefore, the request in this scenario will be done to the yellow queue. We recall the two initially highlighted properties. The symmetry between source and destination is guaranteed as reversing the path is just a chain of sign of mu. A hop that increases mu reaches a hop with greater value than any previous, so it cannot revisit routes. For conditional link, it is guaranteed by the additional rule. All the minimal routes are included together with most of the valiant routes, and many of intermediate length. There may also appear some longer routes, but will only be employed in the rare situation where a packet uses several times a low priority link because of contention. We have a general bound of 4 times diameter minus 3, only reached in extreme cases. Thus, there may be many opportunities along a path when the router can choose between different links, allowing to employ all the diversity of the topology. The focus of this routing algorithm is on large networks. In these networks, it is guaranteed that any router has a neighbor satisfying the criteria. This is a neighbor increasing mu while unless not decreasing it with additional constraints. This is the case of many proposals such as the Dragonfly, the HyperX, Slimfly or projective networks. It is also the case of random topologies or large rares, with these large rares being the case of relevant networks for both supercomputers and data centers. Polarized routing also works in regular topologies such as Tori, if they fall out of the scope. However, it must be noted that this does not work as it is in some topologies or other scopes, most notably the mesh, which is better explained as a composition of paths. In the figure, we show a path topology towards the right is the minimal and unique route. The hosts to the left are allowed, but they reach the corner with no continuation available. One way to address this would be to incorporate the coordinates of the mesh into the rules, but this is out of the scope of the proposal, which is centered in large networks. We proceed now to the evaluation of polarized routing. As topology, we present the tailored result for a random network and a quick glance over 4 different topologies. The random network is a 17 regular graph using 24 Radix routers. Each of the 720 routers having 7 ports to connect servers, giving a total of 5040 servers. The other topologies are a 3-dimensional Hamming graph. This is a HyperX network, a Dragonfly network, the Slimefly based on the MMS graph, and a network of the Levy graph of infinity projective plane. As traffic pattern, we consider the uniform pattern as the basic reference, a random permutation of the server's more realistic scenario, as a pattern to stress a small collection of links, we employ a permutation of the routers to a neighbor router. We will also show the following measures. The average throughput as a basic measure of network capacity. Regarding fairness, we use the Jane index of generated load and the number of paths of each length to understand which routers are actually selected. and the average delay for more details on performance. This bar plot indicates the average load consumed per server, normalized to the server link capacity, while offering full traffic to the network. The base reference are minimal routine, shown in green, and Valiant, shown in violet. Polarized is shown last with thick borders. We observe that polarized routine provides almost the same throughput as minimal routine for the uniform traffic pattern and provides the most throughput for the other pattern. The difference is most notable for the permutation to network traffic, where polarized routine provides 23% more throughput than Valiant. In turn, Polarized is also superior to routine mechanisms that try to emulate Bayesian scheme when the traffic is adverse, as does UGAL. This slide tries to reflect the fairness behavior of the routines. The ordinate is cut at the value of 0.9. This value can be considered already quite anomalous, since it may mean something in the lines of one of its 10 servers is not actually generating traffic, or other possibility being that half of the server is working at half the load than the other half of servers. For uniform traffic, all routines are relatively fair, the most fair being polarized and minimal. In the adverse pattern in the right, this is the traffic to network, polarized is best, followed by minimal and Valiant. But note, but minimal is being fair with all servers generating little load, as they must turn to use the single link between routers. Thus, for minimal, this just means the router is being fair among its attached servers. For the random permutation of servers in the middle, polarized routine appears as the most fair until peak capacity, where that high load becomes unfairly distributed along the several flows. While it is maintained above the 0.9 value, it would benefit of using some throttling mechanism to avoid offering more load than the peak capacity. These are the lengths of paths used by different routines, with greater ordinates for greater number of packets using that number of hops. The plots of uniform and random server permutation are near identical, and the permutation to network notably different. In the minimal line, we see that most pairs are at distance 3, although the diameter of the RRG is 4. We also observe that polarized routine follows closely that distribution, but with a small tail of packets with routes of length up to 8 hops. Although the theoretical bound on polarized routine is of 13 hops for diameter 4, for this specific topology there are never more than 8 hops. In the permutation to network, all minimal packets use, obviously, routes of length 1. KSP, all paths and Valiant do near the same as they do for uniform traffic. Polarized routine behaves quite differently. Having more routes of length 5, this is less than the 6 in Valiant, but also exploiting the single hop paths as much as possible. In any case, under polarized routine, very few packets employ 6 or more hops. Thus, even if some routes can get quite loud, most have very adequate values to the circulation traffic. This adequacy in the length of the routes implies very low average latencies. It is only marginally larger than minimal routing for uniform traffic and notably better for the other scenarios. All these aspects seen in random networks are also true for other topologies. We just picked the average delay for the random server permutation as is in our opinion the more representative measure. It is evident that polarized routing performs better than both minimal and Valiant routing. In the case of Hamming graph or HyperX network, the performance also exactly matches the one given by a very well made specific algorithm. It is notable that there are differences in the actual routes employed by both routines, but only in regards to the use of links that would be otherwise underused. To finalize this talk, we summarize polarized routing as a mechanism that guarantees symmetries and never undoes previous work, while also giving a large diversity of paths. This provides a balanced adaptiveness that translate into good performance in all cases. Polarized routing can be used for almost any topology. Certainly the case for large networks using data center or high-performance computing, some work could be required to make it work on the mesh-like topology used in network on chip. If performance matches or improves the one provided by algorithms derived for specific topologies. This is important for topologies for which can be hard to derive specific algorithms, such as random regular graphs, making the implementation of these topologies more feasible. It can be employed as a whole approach to any network, not just using minimal or valiant routes, but also intermediate ones, offering the best features in each case. That has been the whole talk. Thank you very much for your attention.
All right. Thanks a lot, Christopher. Again, very sorry about there's an echo in the video. We didn't catch that. Really sorry about that. I hope you still can get the whole thing clearly. So let's see. I see there's one question. Let me see from Dan. Christopher, are you there?
I'm here.
Okay, so we have one question from Dan. His question is, how well will this method apply to AHA networks, or does it apply only to fixed networks?
It works in RRGs, so it works in most ad hoc networks. It will depend on how you will the ad hoc network, especially if there are those corners that I show in slide 15. When there are corners, there may be problems. But in most cases, it should work.
I see. All right. Okay, so I don't see any more questions for now. I see somebody's typing. Maybe I saw one of my questions. We have about 2 minutes for questions. So one question, I think kind of follow up the same thing because you mentioned that there's a corners, those kind of scenario, we better to avoid routing to the corners, right? So can you maybe elaborate a little bit more about how it can be avoided, like some possible solutions there? Is this can be taken care of by your algorithms?
The algorithm must be avoided to enter in a corner. And we are exploring different possibilities to see which is the cleanest one to avoid it. If you had a whole topology, it should be more evident what you have to do to avoid it. In a mesh, it is clear which are the corners, the 4 corners, and you must avoid to enter. In arbitrary topologies, it can be harder.
I see.
We're exploring possibilities.
Okay, I guess let's do the last one last question from Bob. The question is there a general mechanism for avoiding routing deadlocks or virtual channels needed?
We're using a virtual channel per hop. There could be another approaches that reduce it, but it will always cost. In the mesh, there are to avoid to use virtual channels, you need to make restriction like like turn restriction. In this case, we allow many routes, and it's hard to avoid using many virtual channels.
Ramon, you have anything to add there?
Yes. Hi, everyone. Good night from Spain. We have here 10 p.m. and then after long day. Just to say, first thing, just to say, I'm very, very grateful to you for organizing this very good conference. We are very happy to attend it and, of course, to be inside with this paper. And then the only thing I would add is that this mechanism works in general, for all the interesting networks, high radix networks, no low radix, for example, for meshes or 3D meshes or something like that. At least right now, it just works on topologies like rings, like torus, like random graphs, okay? But not that special cases in which we have corners and then we enter with the routing in a corner and then we are unable to roll back. Okay, and then the question, I think Cristobal answered perfectly. The question about virtual channels, we are about deadlock. We are using the traditional mechanism of using the virtual channels as a step, this very old solution, and then the number of virtual channels is proportional to the length of the longest routes. This is the typical way to avoid deadlock in this kind of networks.
Okay. All right. Thanks a lot. Sorry, like we have to keep things on schedule. So appreciate Remo and Cristobal for Q&A. So from the audience, if you have any more questions, please post on the Slack channel. We will monitor that questions. So let's move on to the next paper. So the next presentation, the speaker will be Jun Tan. Jun, if I'm not sure if you are on the call, but I will check offline. So Jun Tan is the master candidate at National University of Defense Technology in China. His research interests include software-defined networks and co-design of hardware and software. So he's going to present the paper MBitTree, a fast and scalable packet classification for software switches. So I'm going to play the video here, and I will post the Slack channel for any question you would like to ask the authors. So just give me a second then.
Mr. Chairman, ladies and gentlemen, good afternoon. I am very glad to have this opportunity to attend the conference. My name is Tan Jing. I am from the National University of Defense Technology. The topic of my presentation is MBitTree, a fast and scalable packet classification for software switches. My presentation will include these 5 parts. First, the background of our research. Second, the challenging review. Third, the algorithm we have proposed in this paper. Then, experiments and results on the database. Finally, some conclusions we have got. First, I would like to introduce the background of our research. Packet classification is a key building block of many later assurance, such as quality assurance, network security, police routing, and open flow. A packet case file contains a list of rules, each consisting of multiple match fields and action to taken when packet matches. The purpose of packet classification is to find the rule that incoming packet matches from the list of rules as shown in this figure. The table shows an example open-flow case file. We can find that there are 12 failures.
So is there any issue with the video? It's too, somebody, I see somebody say can hear the voice. Let me try it again.
In the rule,
Then
experiments and results and database. Finally, some conclusions we have got. First, I would like to introduce the background of our research. Packet classification is a key building block of many network services, such as quality of service, network security, police routing, and open flow. A packet case file contains a list of rules, each consisting of multiple match fields and action to taken when packet matches. The purpose of packet classification is to find the rule that incoming packet matches from the list of rules as shown in this figure. The table shows an example open-flow case file. We can find that there are 12 failures in the rule. Current packet classification solutions can be divided into two categories: hardware-based solutions and software algorithms. Hardware-based solutions with TKM have been the dominant implementation of packet classification in industry. TKM provides constant classification time and guarantees high performance, but it comes with some significant limitations, such as high cost and high energy used. In contrast, software-based solutions, also known as algorithm-mediated solutions, have attracted wide attention because of their low cost and flexibility. There are two types of packet classification software algorithm: decision tree algorithm and tuple space search. Our proposed algorithm on MBitTree is a decision tree-based algorithm approach. Packet classification can be regarded as the point location problem in computational geometry. The fields in the packet header correspond to the dimensions of a geometry space, and a packet denotes a point, while a rule denotes a hypertangent in the space. Then, classifying a packet is the equivalent to finding the highest priority hypertangent that contains the point representing the packet. The geometric value of the Ruleset in the table is shown in the figure. In the decision tree-based solutions, the geometric value of the packet classification problem is taken and a decision tree is built. The root node of a tree covers the entire search space containing all rules. Then, partition the search space into smaller subspaces until the rules covered by each subspace are no more than a packet size called bins. Next, we discuss two common techniques to build decision trees for packet classification: node cutting and Ruleset partition. According to the partition method and sorting space, node cutting can be calculated into three major approaches: equal size cutting, equal dense cutting, and bit cutting. Equal size cutting separates the sorting space into many equal sized subspaces, such as hyperclass, while equal dense cutting separates the sorting space into many unequal sized subspaces containing nearly equal number of rules, such as hyperstring. The idea of bit cutting is to extract some discrete bits from the rule, interpret these bits as a number, and use that number as an index into an array of child nodes, such as bit class. The figure shows that the decision tree built by hyperclass and hyperstring. Ruleset partition technique partitions a rule set into several subsets according to the features of rules, which can greatly reduce memory consumption while causing little impact on the throughput of algorithms. Partition Ruleset according to the field size puts small rules and big rules into different subsets, such as the inefficient class. Partition Ruleset using the linear arc find the optimal partition with the help of motion node, such as the linear class. Now we come to the second part, challenging review. In decision tree algorithm, rule replication is the main troublemaker. The meaning of rule replication is that a rule is dispatched to multi-leaf rules, such as rules R9 and rules 11 in the figure. When there are many rule replications in the decision tree, it would yield memory explosion. And equal size cutting and equal dense cutting is inefficient because of that there are serious rule replication in this algorithm. Solutions to the problem of rule replication includes more efficient node cutting technique and Ruleset partition, equal size cutting, and equal dense cutting do not consider the distribution features of Ruleset, resulting in serious rule replication. Compared with them, bit cutting is more flexible, but its performance depends on the bit selection schemes. Researchers has proposed many bit selection schemes. However, there are some shortcomings with them. For example, most of them do not consider the correlation between the bits and easily fall into a locally optimal solutions. Therefore, we need a more efficient bit selection to build the decision tree. Ruleset partition according to the field size is fast and well used. It needs to define a key threshold to distinguish the large fields from small fields. However, it is hard to find the optimal threshold for various types of rule sets. Ruleset partition uses motion ring can partition a rule set adaptively, but it needs a lot of training and takes a long time to coverage to its optimal solutions. So, how to achieve both fast and adaptive Ruleset partition? Third, I would like to introduce the proposed algorithm in our paper. According to the above review, the Ruleset partition can significantly reduce rule replication while causing little impact in throughput. Bit cutting is more flexible compared to equal size cutting and equal dense cutting, whose performance depends on the bit selection scheme. Therefore, we combine Ruleset partition and bit cutting. We proposed adaptive loss partition technique and a multi-bitting scheme to build an efficient decision tree. The framework of MBitTree is shown in this figure. MBitTree builds building decision trees in two stages: adaptive loss partition and multi-bit cutting. The loss partition or cluster algorithms is used to achieve adaptive loss partition. So several subsets are obtained. Then a multi-bit cutting scheme is applied to building a tree for the subset, which selects effective bits to separate rows. In the packed classification, MBitTree searches each tree to find the matching node. To search a tree, we first look at its root node and check the type of node. If it is a leaf node, we just use linear search to get the matching node. Otherwise, we traverse the tree until a leaf node is reached. The distribution of Ruleset has specific features, and the exploitation of them is helpful to build a better tree. We make some observations on access control list, firewall, and IP chain Ruleset. It can be found that the prefix length of IP address tend to be distributed at the edge. That is, a large portion of prefix is located near 0 or 22, as shown in the figure. Therefore, we use a partition-based clustering algorithm, k-means, to partition a Ruleset because of its fast clustering speed and low time complexity, and the IP addresses is used as the basis for clustering. The key of k-means is the selection of a number of clusters and the initial central points. First, the source IP and the destination IP prefix lengths of rows are represented by a point in the two-dimensional coordinate system. And we say the number of clusters k is equal to 4, and the initial centers of each cluster are C0, C1, C2, and C3. Taking the rows in the table as an example, because the bit length of each field is 3, so the initial centers of the cluster are C0, C1, C2, and C3. And the clustering results of rows R1 to R11 are shown in the table. Several subsets are obtained after Ruleset partition. Then multi-bit cutting is used to build a decision tree for the subset. The key problem is how to select the best cutting bits, called effective bits, to separate rows evenly. Two machines are used to select the effective bits: bit separation capability and wildcard ratio. The bit separation capability determines whether the node distribution is uniform on this bit position, and the wildcard ratio estimates the degrees of rule replication. The bit separation capability is calculated as equation 1, while the B01 is equal to 1 and B1I is equal to 0 when the values of the I bit of the node is 0 and the reverse is true when the node value is 1. The problem of rule replication should also be considered since the wildcard is replaced with both 0 and 1. When rules are dispatched into child loaders, we introduce the wildcard to estimate rule replication. The wildcard ratio of I bit is calculated as equation 1, when n wildcard I is the number of rows with the value of wildcard at the I bit position. Considering the bit separation capability and the wildcard region comprehensive, we select these bits with the maximum bit separation community and the minimum wildcard ratio as the effective bits. Taking the cluster 1, rows R1 to R7 as an example, because the second bit has a maximum separation community and the wildcard ratio of this bit is equal to 1. So we choose the second bit and the effective bit to separate rows. The decision tree contrast after the first bit selection is shown in the figure. When faced with large-scale row sets, it is required to select multiple bits at a load to lower the height of tree. In the subsequent bit selection, if we just use bit selection community and wildcard ratio as the selection criteria, it will give rise to the problem of correlation between bits. That is, the value on these bits is only the same, so the results of selecting these bits as the effective bits is the same as selecting only one of them. There are two strategies to solve the correlation problem between bits. Calculate the correlation between bits and select the effective bits from the largest child node. However, calculate the correlation between bits will bring much extra complication. Therefore, we adapt the second result. Select the effective bits from the largest child node. For example, two child nodes are formed after the first bit selection, and we take the left child node and the calculation object in the next bit selection. So the third bit is selected as the effective bits, and the tree produced by MBitTree for rows R1 to R7 is shown in the figure. There are a limited number of trees built by multi-bit cutting. To classify a packet, MBitTree needs to search each subtree to find the matching row. To search a tree, we first look at its node and check the type of node. If it is a leaf node, we just use linear search to get the matching row. Otherwise, we trace the tree using the effective bits stored in the internet until a leaf node is reached. The raw data section is shown in the figure. We used 1 byte to represent the type of node, internode or leaf node. For each internode, we use 1 byte to represent the number of effective bits, and 8 bytes are used for the effective bit information. The leaf node uses 1 byte for the number of rows covered by the leaf node. Both the internode and the leaf nodes use 4 bytes to store an array point. To achieve high throughput, we map the design flags built by MBitTree to a parallel multi-pipeline architecture with n linear pipelines, and each pipeline is used to traverse the design tree and match the list of rows attached to the tree's leaf nodes. Okay, now we move to the part of experiments. We use class bunch to generate the row sets for the experiment. Class bunch includes 12 different scene files in 3 different categories: 5 access control lists, 5 firewall, and 2 IP chain. We generate row sets of 3 different sizes for each scene. We also generate some 500K and 1 mega row sets to verify the scalability of MBitTree. We compare MBitTree against hybrid class, partition sort, and color splinter. We measure 4 metrics: that is memory access, memory footprint, construction time, and scalability. The figure shows the average number of memory access or MBitTree, as well as hybrid class, partition, color sprint. It is clear that MBitTree outperforms better than other algorithms, and the improvement increases as the Ruleset becomes larger. Compared with hybrid class, partition, and color sprint, MBitTree achieves a range of 1.9 times, 2.4 times, and 1.7 times improvement. The figure shows the memory footprint of MBitTree as well as hybrid class, partition, and color sprint. For most Ruleset, MBitTree consumes less space than other algorithms. The low memory footprint of MBitTree means that there is very little Ruleset replication in the chain built by MBitTree. The figure below shows the construction time of MBitTree as well as other algorithms on 100 key Ruleset. It is clear that partition solver is the fastest one among them. In contrast, MBitTree takes a little more time than partition solver because it performs several iterations in the bit selection process. However, MBitTree can still build design chain for all 100 key Ruleset within 1 second, much faster than hybrid class and color sprint. The figure shows the memory footprint of MBitTree from the 1 key Ruleset to 1 mega Ruleset. It can be found that there is a linear relationship between memory footprint and the scales of Ruleset. MBitTree consumes only a few megabytes to build a design chain for 500 key Ruleset. The good scalability in memory footprint makes MBitTree suitable for large class files. Now we come to the last part, conclusion. We provide 2 key contributions. First, we present a new adaptive and faster Ruleset partition. Second, we proposed a new multi-bit cutting scheme to build a short chain, while rarely causing replication. Besides, we also propose 2 methods to solve bit correlation. As a future work, we will explore other available motion ring to partition a Ruleset and implement a high-performance prototype on FPGA. That's all for my presentation. If you have any questions, please feel free to contact me. Here's my email address. That's all. Thank you.
All right, thanks, Jing, for the presentation. Jing, are you there? We probably can have a quick, short Q&A. Hey, Jing, can you, I see you are a co-host now. Can you try to unmute? Just make sure you are there. Hello?
Yeah, I'm ready.
Oh, okay, thank you. So, all right, I don't see any question from the Slack channel right now. So I guess let me ask one quick questions. So in the slide earlier, I think I see I hear you mention that there's some for the current big cutting that approach. The one drawback is they fail to only find the local minima for the threshold to separate the small big Ruleset. So is your approach here can guarantee to find a global optimal threshold, or may have the same issue? If so, like how close you're like the threshold you found, how close it to the optimal one? Hello, Jin, you there? Is the question clear? You're muted, Jin.
Muted. Okay.
Jin, you're muted. Hello.
Let me ask to unmute.
Hello.
Okay.
You're unmuted now. Can you? Yeah. Hey, Jin, are you there?
Okay. I can.
Do you get the questions? All right. Sorry. Like we want to keep things on schedule. Probably there's some technical issues. Really sorry about that. So let's move on. If you have any questions, please post your questions on the Slack channel. You can find it. I put the link in the chat here, and also you can find it on the RD mobile page. So I think that's thank you again for the Crystal Ball and Jin for their presentation. If you have any questions, please post on the Slack channel. I hope you guys enjoying this session. So now, next we have the civil sponsor talk, I believe. So I will hand over to